All right, so let's review our imaginary and complex numbers first. What does the value of I equal? That's a little scary. Please tell me that looks familiar. All right, so I is called an imaginary unit. It is equivalent to the square root of -1. So it is not a real number. It's not part of the real number system. It's its own number system, the imaginary number system. Okay? If you were to square I, that would be the same as squaring the square root of -1. That would just take you back to a real number of -1. Okay? Then we've got I cubed. That's equivalent to -I. Proof on that, I cubed can be thought of as I times I squared, right? Well, I'll leave I as is, and then I squared we just said was -1. I times -1 would result in -I. And then how about I to the fourth? It's going to equal a real number of +1. The proof on that, I to the fourth is the same as I squared times I squared. -1 times -1, which is +1. Okay. Does this ring a bell from your Algebra 2 course? I1, the middle two are negative. Say that again. I1, the middle two are negative. So the pattern repeats every 4 powers of I. That's why I'm only putting up through I to the fourth here. So if I were to carry this down to I to the fifth, it would just simplify back to I. I to the sixth would simplify to I to the second, or -1. I to the seventh would be I cubed, or -I. I to the fourth, I to the eighth would be I to the fourth, which is really 1. Okay? The two that you really need to worry about the most are those two right there. Okay, those pop up a lot algebraically. So as an example, the square root of -27. I could treat that as the square root of -1 times the square root of +27. Square root of -1 can be replaced with I. And then the square root of 27 is 3 radical 3. So that in the end, I end up with 3I radical 3. So that is just another example of a imaginary number. Square roots of negative numbers are in the imaginary number system. Okay? Here I have I raised to a very large power of 35. This is where I would need to employ the fact that this pattern repeats every 4 powers. So I'll take the power, I'll divide it by 4. How many times is 4 going to 35 evenly? With a remainder of 3, right? It's all about the remainder. What this division process has shown me is that I'm getting through this cycle of 4 powers 8 total times, and then the remainder 3 means I'm going into a new cycle 3 times. So I'd end up at I cubed, which simplifies to -I. So it's all about the remainder. The one that always throws everybody off is, what if your remainder is 0? Well, if your remainder is 0, what's anything to the 0 power? 1. So it actually is putting you down here like I to the 4th. Okay? All right, then, last example we have here, these are what we call complex numbers. Okay? Imaginary numbers and complex numbers are 2 different things. A complex number has a real part and an imaginary part to it. So it typically looks like a binomial. But here's the one thing that oftentimes people don't recognize. All real numbers are technically complex, and all imaginary numbers are technically complex. Let me give you an example of that. Would we all agree that 7 is a real number? It's also complex. Would we all agree that 5i is an imaginary number? It's also complex. Okay. So there's a tree diagram system that you can set up for your different real number systems. If we're just looking at the real number system, it branches off into the rationals and the irrationals. The rationals could be the integers, the wholes, and the naturals. But then when you start bringing i's into play, up here you've got the complex number system that branches off into the reals and the imaginaries. So that's just a hierarchy of the different number systems we know. What I'm trying to get at here is every number that you've ever worked with is technically a complex number. Okay, that'll come up later on in this course, actually chapter 4 of the course, where we are asking you to find all of the complex solutions of an equation. Basically any number, whether it's got an I in it or not. Okay, we go back to here though. If you just want to perform a product on two complex numbers, it's just foiling. So 4 times 3 gives you 12. 4 times negative 7i gives you negative 28i. Negative 6i times 3 is negative 18i. And then negative 6i times negative 7i, positive 42i squared. And then you can do some simplifying here. First of all, those are like terms. And then notice the last term, 42i squared. What is that equal to? Negative 42, because I squared is negative 1, right? So that turns into a real number that you can combine with the 12. So 12 and negative 42 make what? Negative 30, and then these two imaginary parts make what? Negative 46. Notice the final result is another complex number. Questions on the imaginaries or the complex number system?